Okay, thanks, Andrew. So I wasn't as bad in the first tutorial, but about this point I can feel the jet lag hitting me. So please, if you have any questions, feel free to interrupt. I'm supposed to summarize the question before I answer it, so also remind me if I don't do that. Okay, so just a quick question. Who here is aware of the algebraic decision diagram? Okay, handful of people. Okay, well then you're gonna learn a lot today. And for those few who are aware of the ADD, who's actually used it? Okay, then for you guys, the second half will be more interesting than the first half. Okay, but it's only two of you. Okay, so I have this thing called decision diagrams. They're pretty well known, at least since the 80s. And I claim that they're critical for automated planning and scheduling, at least for some tasks, not for all tasks, but for some. And I'm going to cover that. Okay, so first thing, what is a decision diagram? Okay, so everyone knows what a decision tree is, right? A decision diagram is simply a DAG variant of a decision tree. So, you know, basically, the nodes can refer to common subdiagrams, right? You don't have to have a tree structure. And typically, at least in most decision diagrams, if you're going to do operations on them, you need an ordering of decision tests from root to leaf, right? So in this decision diagram, the ordering is A, then B. Okay? You don't have to test all variables, but you do have to test in a given order, typically if you do test. And that's quite critical for the operation to be efficient, and if you don't see why, I'll discuss that a bit later. Okay, so what do you use these decision diagrams for? So many things. If your decisions are Boolean decisions, right? These are basically your domain. And if A is true and B is true, and the values of the leaves are 1 and 0, okay, then consider 1 to be true and 0 to be false. Then you're representing a function from a Boolean domain of invariables to a Boolean value, right? Okay. So which handles Boolean functions, and also if you view it in a certain way, where 1 means in the set and 0 means not in the set, you can view a decision diagram also encoding a set of subsets. Okay? And if you did that, there's actually a variant structure I'll get to at the end called the ZDD, which is quite useful for that encoding. Okay? If you just do encodings like this directly, it's called a binary decision diagram. Okay, what if your leaf values, so your decisions are still Boolean, but your leaf values are now integers, and not Boolean values, not just 0 and 1. Okay? Still pretty obvious to represent. This is called the multi-terminal BDD. It would be like if you took the 1s and 0s and concatenated them together. That's the multi-terminal name for sort of a binary encoding of an integer. Or in general, if you let the values just be any integer that you can represent on a computer, right, then it would be a subset of the ADDs, the algebraic decision diagram. Okay? And if your values here were real numbers, 4.35 and the square root of 2, then it would be called an ADD, the algebraic decision diagram. But decision diagrams are nothing more than, at least in this form, functions from some multivariate Boolean domain to either a Boolean, an integer, or a real range. Okay, so it's just a function representation. Okay, so one thing I'll make throughout the talk, one point I'll make is that decision diagrams are very compact for representing many complex structured functions, right? And that's important. But the big deal with decision diagrams is more than compactness. In planning, we need to do operations. I have a bunch of slides on all the operations you need to do planning. And the key thing is that these operations require efficiency, right? So you need to exploit the compactness as you do operations. Okay, so if I want to add two functions f and g, right, what's the result? And how do I build this result without enumerating all possible cases, right? Can I do that efficiently? And the answer is yes. And I'll discuss that. So if you have ADDs, things you might want to do are negate them, sum them, multiply them. I use circle plus and circle times these algebraic operators to indicate that these are operations on functions. They take in a function f and g, and they produce another function as a decision diagram. Okay? So I might want to add two functions, multiply two functions. I might want to take the max of two functions. Okay? If I had BDDs, I want to do logical operations typically. I want to do things like negation, conjunction, disjunction. And ZDDs, again, a variant of BDDs, I want to do things like set operations. F set minus G, F intersection G, F union G. Okay? And doing these operations efficiently for the different places where they're used are really key to efficiency in planning. So it's not just the representation, it's the fact that I can do all these operations critical for planning quite efficiently that exploit the structure. Okay? And that's stuff hopefully by the end of the talk that you'll get an idea for. Okay. So I'm going to start off by talking about many different scenarios where you need operations on functions in general. Okay? And then later, we're going to say, well, why are decision diagrams useful for representing these functions? What can they represent compactly? That's critical to know. And how should you do the efficient operations in practice? Okay. I'll talk a little bit about various extensions of the basic ideas. So I'll cover zeros plus decision diagrams toward the end. These are for sets. Affine algebraic decision diagrams, work I did with David McAllister in 2005 for representing arithmetic structure in functions, and all sorts of other alphabet soup variants of decision diagrams. There's a sequence of letters, there's a decision diagram for it. And finally, who's heard of compilation? So like deterministic DNNF? Handful of people? Okay, these things are quite useful. I'll make the point at the end that if you don't need to do operations on functions, you're willing to compile everything beforehand, then you might want to use these other things instead. Okay? But if you need to do operations that are critical in some domains, you're going to need a decision diagram. Okay? So by the end, if everyone's still awake, you'll have learned all this. Okay, so why are decision diagrams so useful for planning? Okay? The thing is, it's very natural in practice to represent your state not as state 5023 and state 5096 and so on to enumerate all the states, but actually to represent your state as a vector of state variables. Okay? So I mean, I always claim that a natural representation for the state is inherently factored. You have room location, it's a state variable, right? And R takes on values 1, 2, 3, 4, 5, or 6. So right, this is a multi-valued enumerated state variable. You might have doors in each room, right? And the door might be open or closed, right? So you have 7 variables for doors. I don't know. Okay. I think a door for every room, and then the 7th one was down here. And these are Boolean, right? Okay. And what is the world state? Okay. It's really just the concatenation of the robot location vector and the 7 door status vectors. One thing you don't want to typically do in planning is expand this into an enumerated state that gets rid of all the structure of the cross product of the domains of the variables. What would be nice to represent functions over these states directly. And that's one thing that decision diagrams will allow you to do. Okay, throughout this talk, at least up until near the end, I'm going to assume that all the test variables, the domain of the functions are all Boolean. That's just for the talk. In practice, it's not hard to have multi-valued variables like the room location. Okay, all the algorithms I'm going to talk about generalized to the multi-valued case. I'm just going to talk about the Boolean case for decisions. And finally, you might be saying, well, actually, in planning, we use things like strips, PDDL, riddle, if you're really cool. In fact, we have these things, these fluents, right? Robot 1 is at room 6. And in general, most planners in the real world are actually ground. So at the end of the day, they're going to take a variable for at R16. They're going to ground this, and that's going to be a Boolean. And basically, in practice, that's what you're going to work with. All the ground variables as your factored representation. Okay, so we have this very natural representation of the state. What do we do with it? If you're a classical planner, then the state's given by variable assignments, right? The robot's in position 1, door 1 is open, door 2 is closed, so on. Okay, and the planning operators officially update the state. You're in this state, you did this action. What variables change, what don't? Things like PDDL, riddle, compactly encode the state updates. Okay, I would say that the classical planning is dominated by search-based algorithms. I mean, I don't know, is there any state-of-the-art classical planner that requires decision diagrams? I don't think so. Okay, and there's a good reason. It's because search is really dominant there. You don't need to represent functions. You just do some sort of search. And that's fine. I don't want you to use decision diagrams where they shouldn't be used. But I would say if you're doing classical planning, I think you should use search-based approaches. Okay, but there are many other cases where you really do have to maintain functions. And that comes up in non-deterministic and probabilistic planning for sure, as well as in temporal verification. Okay, so you need to compute progressions and regressions. You say I'm in a given state, and my update's non-deterministic. What possible states can I reach, right? So you need sort of a function saying, well, you know, of all states, which are possible. So the range. So the input is the state, the factor representation of the state, and the output is 1 or 0, whether that state's possible. Policies tend, so in probabilistic planning, you have to plan for contingencies, right? There's no straight line plan that will always be guaranteed to get you to the goal. You have to look at what happens stochastically as the outcome of doing an action, and so your plan has to be contingent, right? So in general, you need a policy, which means that you need to map all possible states that you can be in to the best action. Right? And if action IDs are in an integer space, then you can represent that as an ADD, right? Your value is in a state. What's the action I should do in that state? Okay. If you do probabilistic planning like I do, often the value function is quite critical. It tells you what's the expected value you can get for being in a state. So for every state, you assign a value, which is a real value. Okay. So in non-deterministic probabilistic planning and temporal verification, you do end up with these functions, and you have to often reason with them. Okay. And this reasoning requires operations. Okay, so let's dig down a bit more and look at sort of what operations you would need to do. So, you know, I like using graphical models for encoding transition models. So this transition model basically says I have a current state, which is unprimed, and a next state, which is primed. My state is just the assignment to different state variables, which I'm going to assume are Boolean. Okay, the next state, x1 prime, only depends on the previous state, x1, and x2 prime, the next state only depends on both the previous state variables, x1 and x2. Okay, this is sufficient for representing non-deterministic functions. So for example, what values of x1 prime are reachable given the previous state of x1? Right, I can encode that as a function from from the Boolean current state and the Boolean next state to whether it's possible, true or false. Okay, and I could represent sort of that function in this way. So if I'm in state x1 is 0 and state x2 is 0, and you know, is getting to x2 prime 0 true possible? Well, if it's 1, it's true or possible, and if it's 0, it's false. Okay, so non-determinism can be encoded in this sort of model where you have a function from a Boolean domain, right, to a Boolean range. Okay, and if I have the probabilistic case, right, then replace these ones and zeros with probabilities. With the probability of getting x2 prime given the current state being x1 and x2 are false. So 0.7, 0.3, 0.2. Okay. So these tabular representations from these domains to these ranges are sufficient for both non-deterministic and probabilistic transitions. Okay, so that's the representation. Now what do I want to do with it? So in non-deterministic transition systems, you often want to compute forward reachability or backward reachability. So how would I do regression? So let's say I'm in state x1 equals 0 and x2 equals 1. That's my current state. I want to say what next states x1 prime, x2 prime are possible. Okay? So forward reachability over x1 prime and x2 prime. What values x1 prime and x2 prime are possible, right? Be represented in this way. So I've got a function here, say a table for the possible states that I can reach in x2 prime given current state x2, and the possible states that x1 prime can reach given current states x0 and x1. And here you see, given these representations, I just need to do the conjunction of these two to see, well, what joint states are possible for x1 prime and x2 prime. So I need to do a Boolean operation on these two transition functions. Okay? But often in, say, in conformant planning, where you don't observe the true state, you just know you're in a set of possible states, right? You need to say, given the set of possible states I'm currently in, what are the set of next states that I could reach under an action? Okay? And here you have a set S. It's just like this here. I still have t over x1 prime and t over x2 prime. But now for the current state, I have a set saying, well, what combinations of x1 and x2 prime are possible? Okay? And so how would I determine what states are reachable? Well, first thing I'm going to do is a conjunction of all these functions. But then I want to say, I want to existentially quantify out. I want to say if there was some value of x1 and some value of x2 that could reach x1 prime or x2 prime, it's going to be in the result set. Okay? So I not only need to do conjunction here, I need to do an existential quantification of these functions. So how do I do that in practice? Okay. Existential quantification is really easy. I just write it out, right? So if there exists an x such that f of x is true, well, then either it's true for x equals 1 or it's true for x equals 0. So in place of the existential, I can just expand this with disjunctions over instantiations of the variable being quantified. Okay. So to compute for reachability, given a belief state of given a belief state of possible states I can be in, it's just basically a conjunction and disjunction on these functions. Okay. Regression, same thing, except this time I quantify out the next state. Because I care about if I'm in some next state that's possible, say goal state, what set of states that I could be in the previous state that would reach the goal state. Okay? So I'm just quantifying out instead of x1 and x2, x1 prime and x2 prime. But again, conjunction, and if I compile out the existential to disjunction and disjunction. So in non-deterministic planning, you're typically working with functions, and you just need to do logical operations on them. That's the key point. So probabilistic transition systems, you often have a belief state. What's some joint distribution over being in state x1 and x2? And then how would I sample a next state, given that? Here you need to sum out. I won't explain too much here, but you need to sum out. So you need to multiply functions. Take the product of all the conditional probabilities in your dynamic Bayes net, which this represents. You need to multiply functions. You need to marginalize out the current state, because you only care about the distribution over the next state. Okay? So here you need times and sum. And again, how would I sum out over a variable? Right? To sum out over all values of x is literally just instantiate x with all of its values and take the sum of the result. Okay? So to compute this needs multiplication and summation. Okay? I can do belief updates, again, and even decision theoretic regression, which is sort of a regression with an expectation over possibilities and the probabilities of those possibilities. The key thing is all these operations down the probabilistic space require times and sum. Okay? Whereas in the non-deterministic case, it was all logical and an or. In the probabilistic case, it's all times and sum. Okay? So I need not only the representation of the functions, I also need the operations. Okay, and even if you're adversarial, right? So you might be non-deterministic. There's an adversarial that gets to choose the next state. Here you'd actually say you want to choose. You have an adversary that chooses a next state for you to minimize some cost, or to maximize some cost function, or to minimize some value, right? So take the non-deterministic update, but now have an adversary choosing x1 prime and x2 prime so as to minimize the value of the states that you end up in. Okay. Again, how do I do the min function? Well, the min over x is just to take the min of the instantiation of the functions for all possible values of x. Okay. So here I need to do times and min of functions. Okay. And so many other multi-agent formalizations, but typically in the multi-agent case, at least in the adversarial case, you're working with mins and maxes. Okay. So just for some more information on factor symbolic, so typically when you do planning with decision diagrams in these domains, it's called symbolic because you're using symbolic representations of these functions. If you want to look more, these slides will be online, and here's some pointers to the literature. So in non-deterministic planning, lots of work by the Italian guys on non-deterministic planning with decision diagrams, all sorts of verification, et cetera. Probabilistic planning work, the earliest work was sort of done by Craig Boudelier and students Jesse Hoey and Pascal Poupart for MDPs and POMDPs. There's links to that work. Adversarial planning with decision diagrams. Key work that I can think of is the work by Stefan Edelkamp and Peter Kissman and so on, Gamer. That link's here. There's probably other work that I'm missing, but these are sort of some pointers into the literature. Okay, so I'm not going to talk much more in this talk about planning, right? That's up to the domain that you care about. I just basically want to make the point that you need to represent these functions, and at least in the non-deterministic and probabilistic cases, you're going to need to do operations on these functions. I just want to make that point clear. So the rest of the talk is going to be about decision diagrams and how to do these how to represent them compactly and how to do the operations efficiently. Okay, so previously I said you could represent these functions. So forget decision diagrams for a second. You can represent functions with tables. Okay, so this is sort of the first thing that you might try, and it's just worthwhile to think about what would happen if you represent things as tables. Right, so here's a function over 3 domain variables a, b, and c, and here's the value. Just consider Boolean, only 0 and 1. Forget the real values for now. Okay, so what if I wanted to sum out the value b from this function? So say it's a probability, and I want to sum out, I want to marginalize out the value of b. How would I do an operation like sum out on a table? Okay, this is the point where I stop and I wait for someone to answer. So remember, when I sum out, I'm going to instantiate this function for b equals 0. I'm going to instantiate it for b equals 1, and I'm going to sum those two results together. So first question is, what variables are going to be in the resulting function? Yeah, just a, right? Okay, I give the answer up here. Okay, so if a is 0, what value is the function going to take? 0.4. Yep. So if a is 0, right, if I sum out over the value of b equals 0 is 0.1, and the value of b equals 1 is 0.3. So 0.1 plus 0.3 is 0.4, and the other case is 0.6. Right? And if I instantiated these and then summed the functions together, it would be the same thing. Okay, so you can do operations like marginalization on tables. Okay, now if I want for every value of a the maximizing probability for b, what value do I get for a equals 0? Yeah, I take the max of 0.1 and 0.3. So I instantiate b equals 0, I get 0.1. Instantiate b equals 1, I get 0.3. Maximizing value for a equals 0 is 0.3. Okay. The nice thing is, when you're doing maximization, you can also track the assignments. And later at the end, you'll know all the assignments that led to a certain maximization. Okay. If you ever encode the Viterbi algorithm, this is quite useful. Okay, so I can do max. And how about multiplying two functions? Okay, so this function has a and b in it. This function has b and c in it. The result must have a, b, and c in it. So for a equals b equals, okay, for a, b, and c all equal to 0, what's the probability of a and b given c? Okay, I think I heard a whisper. 0.01. Yeah, 0.01, right? Okay, so you can think of operations on tables as kind of like a arithmetic join, right? I'm going to say, okay, I'm going to look at, so we know the output function is over variables a, b, and c, because those are our input functions. We didn't get rid of them. Okay, so you can just go through every case, a equals 0, b equals 0, c equals 0, and you can look up in each of the constituents what probability you took. So if a equals 0, b equals 0, you get 0.1. If b equals 0, c equals 0, you get 0.1. 0.1 times 0.1 is 0.01. So you can just sort of look at the output rows and then compute what the corresponding values were in the input functions, right? Because this must be the union of all the variables in the inputs. It's kind of like an arithmetic table join in a database. So if I do this for times, the cool thing is I can do it for any operation, minus, max, and so on, right? If I did the max of these two functions, I would just take the max of 0.1 and 0.1 to get this. Okay, so first observation is that all discrete functions I'm talking about that I discussed previously for non-deterministic planning and probabilistic planning can all be represented as tables if you want. Okay, and all the operations are directly obvious, right? The summing out a variable or maxing out a variable, right? Or all the binary operations. Like you could go out right now and implement it, right? And it takes a half an hour. Okay, so that's the end of this tutorial, right? We're done. We can represent the functions, we can do the operations, right? What else is there to do? So why aren't we done?
The reason we use factored representations for everything is that this blows out.
Yeah. Okay, this becomes extremely large, right? If you sum two functions and the result has 20 Boolean variables in it, how many rows do you have in that table? To the 20th, right? Yeah, OK. So, and I always point out, like, imagine a building where you had 40 doors. In fact, I think the next slide does this. Yeah, here we go. Right. So, you got 40 doors. And all you care about is whether each door is open or closed. Right? Pretty trivial domain. Like, if robotics wouldn't get off the ground if you could only represent whether the doors are open or closed. But if you just had 40 doors, and you wanted to represent a value function in probabilistic planning, you would need 2 to the 40th states. Depending on your representation, it's around a terabyte of memory to represent a value function over 2 to the 40th states as a table, right? But it's only 40 doors. Like, I mean, AI would not get off the ground if we use tables. So, I mean, you obviously need structure somewhere. It's not always decision diagrams. It can be other structures, but you need structure somewhere. So one reason we need something more compact than a table is for space considerations, right? You can't even represent these functions if you use tables. And the other thing is time. Like, even if you could represent these functions, right, sometimes if you've got to iterate through all rows or all combinations, it just takes way too long. Okay? So in general, you would like something more compact than a table for space and time reasons. OK. So first idea is trees. So this is a function I just had on the previous slide. We can represent it a bit more compactly as a tree in this way. So if there was no structure in this tree, you basically see an exponential tree. It would have A, B, and C, and 8 total leaves. However, you see that it's actually a bit more compact than that. The reason is because when A was true, right, the function value did not depend on the value of B, right? Okay, and that's called context-specific independence. For a certain instantiation, a certain value assignment to one variable in a function, the function becomes independent of some other variables like B. So in the context of A equals true, the function is independent of B. It just depends on C. Okay. So trees nicely exploit things like context-specific independence. But they're still not minimal. Can anyone see how to make this function more compact? What's not minimal about it? Yep. Okay. So in a tree, I couldn't share them, right? Because you can't have a DAG structure. But if I was just willing to say, can I merge? Oh, darn it, I lost one of my animations. Right? So what you want to do is you want to merge the C's together. Basically, have a true point right here. Okay, and it's even more compact. Right? So decision diagrams, as I'll show you, do two things. They not only exploit context-specific independence, which trees already do, but what most people miss when they write so most people, when they write about decision diagrams in literature, mention CSI, context-specific independence, but they forget to mention that you also just get to share a redundant substructure, like the fact that these two trees are shared. Okay. So how would I automatically detect, how would I automatically construct the minimal DAG for this function? I'll discuss the algorithm a little bit later, but it's nice to look at it graphically first. Is there a simple algorithm that's sort of linear in the number of nodes that would find the minimal encoding for this? Good, right? So you see the idea with building a canonical minimal decision diagrams is you start from the leaves, and you recursively build or reductively build upwards. So the first thing I'm going to do is I'm going to merge the zeros, right? So I have a DAG now. All my branches that point to 0 point to the same leaf. Okay, and I'll merge the ones as well. Okay. Now that I've done this, it's pretty easy at the next level up for the C's to determine which functions are identical, right? Because if I have the same decision variable and the same true branch, by the way, sorry, the solid is true and dotted is false, so you didn't figure that out. If I have the same decision variable and the same subfunction for the true branch, same subfunction for the false branch, I must have the same function, right? These two nodes are exactly identical. So I don't need both, right? I can merge them. So you start at the leaves merging, and then you go up inductively, level by level by level, and you merge every level. Okay? So I merge the C's next. You get that. And the result, if you do that all the way up, is called the algebraic decision diagram. It's, for the given ordering, it is minimal and canonical. Every function for that ordering that's identical must have this structure. So it's really quite cool. So if you encode every node with an ID, you can just say, you can just look at whether the IDs of two nodes are identical to see whether they're the same function. Okay. So if we start off with a tree, we can easily, in an ordered tree, we can easily apply this algorithm to create the minimal canonical algebraic decision diagram. So you might ask, well, what if my input was an unordered tree? I'll get to that later towards the end. You can also compile that efficiently. Okay, but that's the process of building the ADD compactly, but we also want to do operations. Sorry, I get ahead of myself. So before we get to operations, one thing you might ask is, well, what functions exactly do ADDs represent compactly? And let's just briefly take the BDD subset, so the Boolean function subset. So and or, right, can be represented compactly by decision diagrams, but also by trees, right? You know, I don't really care that I split off different nodes for the zeros. They're still within some constant size of each other. But one place where there's an exponential separation between trees and ADDs is for functions like the XOR function, right? So as a tree, think every path from root to leaf would be a different tree branch, right? And so the question is, how many total branches are there in this decision diagram? Well, an exponential number because of the recursive referencing structure. So the XOR function, and Randy Bryant pointed this out back in the 80s, is a linearly sized decision diagram in terms of the number of variables in the XOR, but as a tree, it's exponential. Okay? So in some cases, like XOR, there is an exponential separation between tree size and the ADD size. So that's pretty cool. Okay, so that tells me I can represent functions compactly. I told you previously that I can find those compact representations in linear time, the number of nodes in the tree. That's pretty cool. Now, how do I exploit structure in these functions when I do operations? So let's say I want to multiply these two functions, right? So there's a naive way to do it, which is build the table for this decision diagram, build the table for this decision diagram, do the multiplication I showed you earlier on the tables, and then convert the table back into a decision diagram. Okay, that's correct. But if you have 20 variables or 40 variables in your decision diagram, it's going to take forever, if you can even do it in memory. Okay, so how do I directly exploit the structure of decision diagrams to do these operations directly? Okay, so the key, and here is why the ordering is critical for decision diagrams if you're going to do operations. What I'm going to do is I'm going to take the first variable in my variable ordering that's common to both decision diagrams. In this case, that's A. Okay? And I'm going to recursively build out the result. Okay? So I said I have A here, and if A is true, right? Well, I look up, well, if A is true here, I get in this subdiagram here for C. If A is true here, I get this subdiagram here, which is 0. And what goes here at this leaf? 0 times this function is 0, right? That's easy. So for certain identity operations, this is quite efficient. Okay? If A is false, it's a little bit harder. So if A is false, right, I'm looking at the other branch recursively. Then I get to this subfunction here for B, and I get to this subfunction here for C. Okay? I need to multiply these. Now, do I know the answer immediately? It's not as easy in this case. So what do? If you don't know the answer immediately, well, you recurse again. So I say, OK, I'm here at B and I'm here at C. Which is the earliest variable? Earliest variable is B in my ordering. Assume it's A, B, C. Okay? So I'd choose B, and I recurse. If B is true, I get to this function. And if C is true, I get to this function. And I recurse on C again. Finally, I'm at the leaves, right? C true, 2 times 1 gives me 2. And false for C gives me 0 times anything is 0. Okay, and so on. So the key is that you follow the ordering and sort of recursively instantiate the diagram. And there are many places to prune and to avoid computations. Okay. Now the question for thought is, what's the complexity of this operation? What's the worst case running time for this multiplication operation? Assume that both of the input diagrams have, well, assume I have m nodes here, and n nodes in the second operand. What's the maximum number of nodes that I would need in the resulting function? Or what's the maximum number of nodes that I could produce? I have m here and n here. Can it blow up exponentially? Can I have m to the n or n to the m or something? Huh?
Order
Yeah, yeah. So or order mn. Yeah, because yeah. And that's actually a really loose upper bound. In fact, Bryant proves in many cases they're much tighter bounds. But it's really easy to see the m times n bound, because every time I analyze a pair of nodes in these two diagrams, I'm going to produce at most one node in the result, right? So how many pairs of nodes are there between these two diagrams? M times n. And every recursive function call can produce one in the result. Okay. So the nice thing about the complexity of these operations is they are bounded polynomially in the input size. Now, if you do 1,000 of these, right, things can still blow up. And you do tend to do 1,000 operations in practice. But at least one operation will stay fairly compact. And often it's more like, in practice, you see more like m plus n, not m times n. OK. So 4 different operations of planning. We need compact representations of these functions with Boolean, integer, or real-valued ranges. We need efficient operations. Right? Decision diagrams are quite a promising candidate. Okay. In fact, I mean, there are cases where tables won't get off the ground, but you'll get quite far with decision diagrams. And many people realize this. OK, and I'm not claiming that decision diagrams solve all problems. I mean, you can often easily construct problems where these things will blow up, but they have been quite useful. And I mean, they're provably, you would never do worse than the tabular approach. The worst thing you'd get is an exponentially sized tree, right? All possible paths to the leaves were instantiated, but that's nothing more than every row in a table. So you can't really lose by using a decision diagram. OK, so let me see. It's 4:30. Andrew, we have till when? 5:05. OK. So let me just go quickly through some of the operations a little bit more in depth. These will be in the slides, and you can look online later for more details. OK, so there are 2 main operations that you need to know for decision diagrams. One's called reduce, and the other is called apply. Reduce is for producing a minimal diagram, and apply is for an operation on diagrams. Okay, so reduce tells you how to build a canonical decision diagram. Okay, so let's say I have this input tree. Just to formalize a bit more what I said previously, how would I implement that in practice? You need to keep 2 hash tables. One hash table will hash from your leaf values, let's assume an ADD, so the leaf values are real, to a unique ID. So if I give you 2.3, you can say, here's the node for leaf value 2.3. It often helps actually to approximately hash sometimes, if you don't care about an epsilon error. And then, so that's for the leaves. And then for all the internal nodes, I need to hash from the decision variable and the left branch node ID and the right branch node ID, or the low ID and the high ID, right, to a canonical ID. If you have these 2 hash tables set up, it's pretty easily in 15 minutes to build a canonical, to write the code to build a canonical decision diagram. So what happens here is it's a recursive algorithm. I start at x2, I get x2 true, it's here, I get here, and I say, OK, I've already hashed the leaves to unique IDs, and now I need to hash the tuple of x1, true branch 1, false branch 0 to an ID. So I'll create an ID 2 for this node. Okay. Now once I've done that and I come down to the right branch here, I need to hash again x1, true branch 1, false branch 0. It actually already exists in my hash table. It was already labeled 2. Right? And so I realized that these 2 functions have the same ID label. So you get to this diagram here, right, where you've got x2 pointing to both branches, true and false, point to x1. Okay. There's another function that you use to say, well, get me the canonical version for x2. And the first thing it says is, are the true branch and the false branch equal? Because if they are, you don't care about x2. Whatever value of x2 you take, you're going to get to the same subfunction. x2 doesn't matter, and so if the branches are equal, then you just get rid of it, and you get this function x1. So all you need is simple recursion and 2 hash tables, and you can build these things compactly. Okay? And literally, I've taken my Java code, and I've converted it to pseudocode. This is the reduce algorithm, the recursion. Right? Reduce the high branch, the low branch, and then get the canonical result. And then it calls this helper function. So it takes about 15 lines of code without comments to implement that. Okay, Good. And so what's the complexity of the reduce algorithm? Actually, one thing I want to, it's critical in the reduce algorithm to always see if you've reduced a node already before you recurse on it. If you didn't have this thing called a reduce cache to say, have I already reduced this node here, then in this case, you'd end up doing an exponential number of reductions. But if you just always record, have I seen this node? So you came down this true branch, you got to x3. Later, you come down false, false, you get to this node again. You say, have I already reduced this node? As long as you cache that result, then the reduced complexity is linear time. But it's critical to have a cache to say, have I already reduced this node? And the XOR is a critical example of if you don't do that, what happens? Things can blow up exponentially. So reduce is linear time in the size of the input DAG, and it produces DAG that's strictly smaller, right? The canonical, or strictly equal or smaller, the canonical form. Okay, it's pretty easy to reduce. It's pretty easy to prove that this is a canonical representation. You do this by induction on the variable order. So the base case is you say, do I have a canonical representation for the functions with 0 variables, so just the leaves? Okay, pretty easy to show that if you have a hash table that returns a unique ID for every leaf value, then yes, that's true. Then inductively, you assume that your functions are canonical for k-1 vars. You say, are they canonical now for the case of k-vars? So for the case var, you only add one decision and one true branch and one false branch. Okay? And if the true branch and false branch are different functions, there's only one representation of that function. You store it in the hash table. Okay? And if they were the same function, then remember you get rid of vk because it's not important. And then you already proved that then this is inductively reduced or canonical. So it's a pretty straightforward proof that the reduced algorithm does give you a minimal canonical representation for a function. Okay, so proof will be on the slides for you to look at later. Okay, common question is, how important is variable order? Right? It's actually extremely important. So this is from Bright's original paper. In fact, the first thing you should do if you're learning BDDs and ADDs is go back and read this paper. I mean, the reason why it was one of the most cited publications in all of computer science is because it's quite beautifully written. Right? You'll learn a lot from reading this paper. So Bryant gives these two examples for BDDs. What he's done is this variable 1 is actually different from this variable 1. So all you have to understand in looking at these two functions, they're the same functions, but he's reordered the variables. And basically what you see is that on reordering, the function size can blow up. Right? So it can be critical to find a good variable ordering in practice. However, I would say you typically want to find this variable ordering before you do your operations. If you try to reorder a diagram to be smaller, you're going to waste a lot of time in practice. So packages do support dynamic variable reordering, but typically it's not worth the effort to do it. If you want to find a good variable order a priori, basically you want variables close by in the order that have strong interactions. So for example, if you have a graphical model representing constraints between variables, then you want a load tree with ordering of variables across that graphical model. That tends to produce, in practice, smaller diagrams. That's not a proof. Okay, if you did want to reorder dynamically, there's a pretty nice algorithm for doing that called Rudell's sifting algorithm, where basically you do reordering by swapping variables locally in your variable order, right? You can get from one order to another just by local swaps of reordering A and B in the order. So imagine some function looks like this, has a bunch of pointers coming in, and then it routes through A and through B. Okay, how do I reorder B to go before A? Well, as long as in memory I can replace what everything is pointing to here for A, so it helps to be probably in C at this point. Then I can just put B in A's place and just reroute. Well, here if A was true and B is true, I get ID 1. If B is true, then A is true, I get ID 1. But if A is true and B is false, I get ID 2. So B is false and A is true, I get ID 2. So the thing is basically you just have to sort of replace what's at the memory here, it's being pointed to, with the test B, and then create the new nodes for A, and then just have those point to the existing subfunctions. So it's pretty easy to locally reorder with swaps, and with any sequence of swaps, you can reorder the entire diagram. This is what's used in practice for dynamic variable reordering, but again, it's a very expensive operation to do tons of swaps to completely reorder. And the heuristic methods for sort of minimizing function size with this method are quite expensive in practice. So you can do it, but I don't recommend it. OK. So that's reduction and sort of producing minimally sized diagrams. The other algorithm, and then I pop up to a high level after this, is the apply algorithm. So how do you do any binary operation on two functions? So again, recall that we have two functions. We want to do multiplication. We just recurse on the true and false branches, right? Okay. What if I had done the max of these two functions? What would have changed? Instead of times, I did max. Is it the same recursion? Yeah. So basically, the operation only matters when you're doing operation with the leaf nodes, right? Once I get down some branch to 1 and some branch to 0, then I apply the times. Now sometimes, remember when A was true, I get 0 here, and 0 times anything is 0. If this was max instead of times, it would be max of 0 in this function. So what result would I put here? Not 0 anymore, right? It's not 0 times this function. It's max of 0 in this function. Yeah. So if you can always recursively store, you can always label nodes with the min value and the max value inductively from the bottom up. So you would know that the value of this node is a min of 0 and a max of 1. And its min is greater than or equal to the max of this function, right? So you could actually, once you get here, just replace this node with this function without even looking at it, right? You don't need to recurse on it. You just put it here. But the key thing is that when you change the operation, you just have to change the definition of what you do once you get to leaf nodes, right? And if you don't care about pruning at all, like I'm doing here, or any efficiency tricks, you would just need to basically take two terminal nodes and just return their result. So whether it's plus or times or max, doesn't matter. The apply operation is always the same operation. Okay. So all binary operations have the same algorithm, and that's pretty cool. Okay, so how do you do this in practice? So there's two cases. There's a case where I'm doing an apply operation on two functions that have matching variables. So f1 and f2 both start with v1. And in that case, I want to say, well, in the resulting function, I look at when v1 is true. And that's going to be this function here. I'm going to apply the operation to this function, f1h, and this function, f2h. Okay? That gives me the subfunction when v1 is high, high being true. Okay? Likewise, okay, and so I can construct half of the result. Okay, then for the other case, when v1 is false, I do the apply operation on the false branches. Right? That's this one. That's this apply operation. And finally, I call this get node on the result, which basically just checks, does fh equal fl? Right? If these two functions are the same, I would just return one of them. They're the same. Otherwise, I look up at my hash table and I say, OK, do I already have a representation for this test in these two branches? Okay? So that's the applied recursion if your two functions have matching variables. The other case is if they have different variables, right? One has v2, the other has v1. Let's assume that v2 occurs earlier. Yeah, sorry. v1 occurs earlier in the ordering than v2. So when v1 equals true, I move down in this diagram, right? But when v1 equals true, it didn't affect this diagram. I still stay at this level in this diagram. And I apply the operation to this function here and to this subfunction here. Okay? Now that gives me half. And again, for the false branch, I move down to f2 because I'm recursing on this variable, but I'm not recursing on v2 yet. So I just do the apply operation between the two blue-enabled loads. Here, I get the result, and again, I apply get node. Okay. So again, to turn that into code, it's just this function here. So it's like 10 lines. You get the earliest variable in the ordering, and that tells you what you set your functions for recursion to, and then you apply, and then you get node for the result. Okay. So again, this is about 15 lines. And literally, I mean, if you know what you're doing, you can literally write all the ADD code in a half an hour. I mean, it's really beautiful. Beautiful algorithms, very compact, and very, very easy to write. OK, and again, apply works for any binary operation. We already explained why. OK, I already mentioned that the apply operation has this upper bound of the product of the sizes of the input diagrams, right? Again, it's a pretty loose upper bound. It's more like F1 plus F2 in practice. And you can prove the results canonical. If the input diagrams are ordered, the result's canonical. The result's also ordered. OK. Now, if you remember previously, back to the beginning of the tutorial, I talked about the fact that you would need to do like marginalization or existential quantification or minning over variable. And a key thing to do when you're doing these operations is to restrict a variable. So what if I have f of x, y, z, and I want to restrict f to z being equals just 0? Okay. For all the max out, marginalize out, and so on operations, I need to do these instantiations. So it's really easy. I just modify the reduce algorithm so that as soon as I get z equals 0, rather than reducing each side, I just return the reduction of the assignment for z, which is 0. So I just return the reduction for this side. So you can easily extend the reduce algorithm to handle restriction of a variable. Okay. So if I reduce this with z assigned to 0, I just get obviously this sub-branch. Okay. And then once I've done that, I can do all these operations. Like summing out a variable is just restricting to 0, restricting to true. Right? So I restrict it to x to be true, x to be false, and I sum those results. And that's how you implement the sum over x operation in practice, right? And so for minning over a function, or minning out a variable, or essentially quantifying out a variable, which is just the OR operation, I just need to do restriction. And how am I doing this plus? What operation allows me to do plus? Reduce or apply? Apply. Okay, so you're just doing restrict and then apply whatever operation you care about. Is it min? Is it or? Is it plus? And so on. So you can do some cool things. One thing, when I'm working with students who are working with ADDs, one thing they do is they build their functions very inefficiently. Okay, so there's one key thing that you have to know to do is when you're building a function from an expression, you should just do apply operations exactly as the expression would apply them. Right? So I'm summing out over I equals 1 to n of xi. This is the function. It's not the marginalization operation. For decision diagrams, this is actually the function is just the sum or the count of the xi's that are true. Okay? How would I build this in practice? Well, my students often build a table, okay, and then they'll compress the table into an ADD. But that's really inefficient. What you should do is you should compute the indicator for xi. So x1 just says, if it's true, I get 1. If it's false, I get 0. You do that for all of your xi's. And then just use the apply operation to sum them together. Okay? And the result is quadratically sized, so you don't have to build an exponentially sized table to get to the quadratically sized result. So exactly as you view the binary operations in this expression is exactly how you should use the apply operation to build the function for this expression. So here's another expression here, right? x1 plus x2 plus 4 times x3 times x4. Again, go down to the leaves of the expression, build the simple ADDs, and then every time you hit a plus or times, you use the appropriate apply operation. So use apply to build functions directly from the expressions, right? And it guarantees you compactness and efficiency in building them. Okay, I said earlier I would tell you how you could build a decision diagram, an unordered decision diagram, right? It's definitely not canonical because it's unordered. And how you can build an ordered decision diagram from that. Okay? And you can do this recursively with the apply algorithm. Okay? So I'm only going to focus on the recursion here. You just do it bottom up. Okay? So at some point, I'm at level, I'm at z in the variable ordering. And z has true branch ID 1 and false branch ID 0. But I know, or I hypothesize that z may be out of order. Maybe there's some variables x and y that should occur before z in the ordering. Just with apply, how do I reorder this diagram? How do I get z in the right order? Okay? So the result of this operation is in the right order, and it is equivalent to this one. So let's go through this. So I can take an indicator that says if z is true, I get 1. If z is false, I get 0. And I can multiply the indicator by the true branch, right? And I can take the indicator that says if z is false, I get 1. If z is true, I get 0. And I can multiply that indicator by the false branch. Okay? So this branch is only non-zero when z equals 1. This branch is only non-zero when z equals 0. I can sum them together. Arithmetically, this is equivalent to this, right? Okay. But if you look at this, if I've inductively assumed that the subdiagrams are ordered, and by building from the bottom up, you can always inductively assume that. So if this is ordered, right, is this diagram ordered? It only has one variable. It has to be ordered, right? So this here is arithmetically equivalent to the left-hand side here. And all of the operations, all the functions in it are ordered, provably. And the apply operation preserves the ordering, right? So the result of this must be ordered, must be minimal, and must be equivalent to this left-hand side. So it takes 4 lines of code to canonically reorder an unordered decision diagram. Right? And this will be in the slides if you want to look at this later. It's really cool. OK. So that's all my tricks for ADDs. And basically, the BDD is just a 0-1 subset. So if you can do it on the ADD, you trivially have the operations for the BDDs. If you're doing disjunction or and or set, sorry, if you're doing or and or not, then again, we're just looking at the leaf nodes when we do these operations. OK. So up to this point in this tutorial, I've covered why you might need decision diagrams in non-deterministic planning or probabilistic planning. I've covered the ADD and the BDD, which are sort of your core diagrams. I've covered the operations. And so from this point in this tutorial, I'm going to say what other decision diagrams are there. Are ADDs and BDDs enough? Or are there other things that might be more compact in other cases? Okay? And the answer to that question is yes. Depending on your application, there might be alternatives to the ADD or the BDD that could be more useful. Okay, I'm going to cover what those are. I realize for a lot of you, I don't know if we want to take a stretch break or something, but this is a lot of material. So who's happy to go on, or who wants a quick break? So who's happy to go on? OK.
May I ask a question?
Please.
It just, my head is interested, but when you were talking about all right. So you mentioned, I mean, the operations that you were showing before, they are polynomial in the size of the diagrams?
The input diagrams.
Yeah, but the size of the input diagrams, they're exponential on the number of variables, right?
In the worst case. I mean, if they're exponential on the number of variables, then you didn't gain anything by using a decision diagram.
Yeah, exactly. So I was just asking myself, so when you were talking about that expression, the sum over xi for like an enormous number of various i's, and then you said, well, why exchange? This expression only has, if they're binary, it can only have n possible numbers. So once you do the reductions, you will definitely have a much reduced diagram.
That's great proof that at most you're quadratic sized. Good.
Yeah, but I mean, how can you? I mean, wouldn't you have, if you use that expression that you put down there, the combination of the diagrams, wouldn't you have to end up with an exponentially sized diagram, and then from that point you reduce? You do that recursive thing?
No. Okay. Because the apply operation at every recursion produces a canonical minimally reduced result.
Okay. So for each one, after each one of these operations, you would like refactor the thing.
Yeah. So the only time you call reduce is is in the beginning. If someone gave you a tree that was ordered but a tree, then that's the point at which you call reduce. Okay. But if someone gives you a function and you can build it with apply, you can do everything with ADDs only using apply. And every intermediate result of apply is always minimally reduced.
Okay. Thank you.
Good. That's a good question. Any other questions? OK, so there are these things called zero-expressed BDDs. If you've heard of them, you may also have heard that they're really useful for doing set operations. And the question is, why is that? First of all, what are they? And second of all, why is that? OK. So imagine that I wanted to represent sets of subsets. So I have variables a, b, and c. And I want to think of sets over a, b, and c, right? So the set with a and b in it, set with a and c in it, and the set with c in it. OK, if I represent it as a BDD, I can do it like this. OK, so I want a and b to be in the set. A is true, and b is true. And c is true, it's not in the set, right? A, b, and c is not in the set. But if a is true and b is true and c is false, then a, b is in the set and you route to 1. So basically, when you route to 1, it's in the set. When you route to 0, it's not in the set. And this is the BDD representation of the set of subsets. OK, but is there a more compact representation? If your sets are relatively sparse, that is, of the power set, you only have a sparse subset of the power set, then the ZDD can be more compact. So this is the ZDD representation. Note that when A is true and B is true, you don't have to route through C. Okay, why? Because you suppress the zeros. You automatically assume if you don't encounter a variable that it is false. So if I get A true, B true, then I'm assuming that on this branch C was false. In fact, if I wanted C to be in the set, then I would actually need this node. And I'd have to route both branches to be 1. But again, the key difference is that here I had to say for every combination of A, B, and C was in set or outside of the set. Here, I assumed that because I didn't hit C on my traversal from root to leaf, that it was set to 0. Okay? So again, if you have a sparse subset of sets, then this can be a bit more compact. Now, the thing with set operations is I don't want to do and, or, and not. I want to do intersection, union, and negation. Okay? So how would I do that on this representation? OK. So I'll get there in a second. The first thing I want to say, though, is that the ZDDs are not a universal replacement for BDDs. Here's a function. By the way, here's the paper you should read if you want to read about ZDDs. And from this paper, here's a function that's a Boolean function. Here's it as a BDD, pretty compact. This Boolean function, though, as a ZDD is quite large. Okay. So if you have a Boolean function, you probably want to use a BDD. If you have a sparse set of subsets, you probably want to try using a ZDD. Okay. So how do you modify the apply algorithm to work with this zero suppression? It's pretty straightforward. What if I want to do the intersection? Okay. Well, just like for the other binary operations, I say, well, if x is true, so imagine that I have f and g. Now I'm recursal on x. Then if x is in the set, then I want to take the intersection of the x true branch of f and the x true branch of g. And if x is not in the set, I want to take the intersection of the false branches. So again, from here, I get to recurse on the subbranches and the subfunctions of f and g, just as I didn't apply. Although, at first I was looking at this, I said, I don't think this is correct. I would think that if x is not in the set, you might need to take all possible combinations from f and g. But I realized, no, that's not true. So when you're doing the intersection, right, x has to be, for a given path, which is a set, x either has to be in the set for it to be in the intersection, or it has to not be in the set to be in the intersection. So on recursion, this is what you want to do. So that operation is fairly straightforward. If you want to do a union, however, it's a bit more complex. And I don't want to explain that online, but I want to say the best explanation of all the operations I've seen for ZDDs is actually given by Don Knuth. So Don Knuth every year at Stanford gives a Christmas lecture. And for 2 years in a row, he gave lectures on BDDs and ZDDs. And it's absolutely, if you want to learn all about ZDDs, and more even that's more than is in this paper, just sit through this 90-minute lecture that's online. If you can't find it, let me know. But he'll tell you how to basically do all the operations, all the set operations on ZDDs. For intersection, it's obvious. For union, it's actually a bit more complex. But you can do it. OK, so if you're working with sets, you want to consider using ZDDs. If you're working with arithmetic functions that tend to have additive or multiplicative structure in them, they were constructed from arithmetic expressions, then you want to consider using the affine ADD. Okay? And this is work I did back with Dave McAllister back in 2005. The paper wasn't cited for the longest time. Around 2000, it got a lot more citations. So some folks in Europe finally picked up on it. Okay, what was the motivation for this work? Imagine that I have the ADD for this reward function. Sorry, I was looking at MDPs at the time. So what you'll notice is this is an exponentially sized tree. Okay, and you can actually prove it pretty easily because this is sort of like a binary valuation of A, B, and C, right? And you see that for every combination of A, B, and C, you get a different value. And if you have a different value at every leaf, there's no possible way that you could reduce this diagram, right? Remember that reduction started by merging the leaves and then reduced upwards, right? But if you can't merge leaves, you can't reduce your function at all, right? So provably, there is no compact ADD representation of this function. It has to be exponential. If it was A plus B plus C, it would be quadratically sized. But this particular expression is going to be exponentially sized. Okay. Likewise, if I exponentiate gamma to the 4A plus 2B plus C, you get the same thing, right? You get 8 different leaf values, and there's no way to compress that. Okay. It's actually funny. You would think maybe in MDPs or something I'd be working with additive reward, and that was the reason I did this work. It turned out I realized that value functions tend to be multiplicatively factored. And that's completely an errant observation when I just looked at some value functions and they had really compact affine ADD representations. This example 2 actually does really happen in practice, if you're wondering. OK, so Dave and I were wondering, I mean, this expression is compact. There should be some decision diagram that sort of encodes the compactness of this expression directly, right? Like, why not? This should be trivial. So we said, well, what if we label the edges of our diagram with affine transforms? So every edge is labeled with an offset C and a multiplier B. And the interpretation is, if A is true, then I evaluate the subfunction, and I multiply it by B1, and I add in C1. So if A is true, the resulting value is C1 plus B1 times F1. If A is false, I get a different constant offset and multiplier, C2 plus B2 times F2. Okay? So we call it the affine ADD because we have affine transforms on the edge. Okay. Now, the thing with decision diagrams is if you just allowed any affine transform on the edge, there'd be an infinite number of ways to represent the same function. So what we actually need is some way to define canonicity. Okay? And David's idea was we should just restrict every function of a min of 0 and a max of 1. So if you do that, right, you get this function instead. So this function, it was 4 plus 0 times 0, max of 4, or, sorry, it was 4 plus 0 times 0. So on the true branch it was 4, and on the false branch it was 2 plus 0 times 0, which is 2. So its min was 2, its max was 4. If I want to normalize that to be 0, 1, I want to subtract off 2 and divide through by 2. Okay? So if I subtract off 2 from the constants here, I get 2, 0, and 1, 0. And divide by 2. So sorry, I get 2, 0, and 0, 0. And I divide by 2, I get 1, 0, and 0, 0. But if every function has a min value of 0 and a max value of 1, the problem is, how do I get back to the range of 2 to 4? So now I need some top-level affine transform, 2 plus 2 times, to give me the min value in the range back. Okay? But the idea was every function except for the very top input affine transform, every subfunction has to be a min of 0 and a max of 1. Okay? And just like I did here, it's easy just to identify the min and the max and subtract off the constant for the min and divide through by the range. And just put that up here. Okay, so it's pretty easy to do this in practice. And then when you do that, right? So you can modify the reduce algorithm that I showed previously to do these transformations. And what you find is you give a disinput diagram, and by the time you end up reducing, you get this sort of linearly sized result. Okay? Now what you do note, in a BDD, you can't have branches going to the same subdiagram, right? The one node can't have branches going to the same subdiagram, because if you did in the BDD or the ADD, you wouldn't need x2. Because the affine transform is edge dependent, now you actually can have the edges pointing to the same subdiagram, right? You can't necessarily get rid of x2 here, because depending on whether x2 is true or false, you get different affine functions. Okay? But the key is, with this definition of normalization, that every function is 0, 1, you can just modify the reduce algorithm to enforce that, and you get these minimal diagrams. So back to the beginning example, right? This function now, as an affine ADD, is linearly sized, no matter how many values I have in it. Because basically, the coefficients got now encoded on the edge, right? That's what the affine transform gives you. So you are really almost directly encoding this expression in a diagram. And likewise for the other function. Okay. So now these functions that were exponentially sized as ADDs are now linearly sized as affine ADDs. So there's an exponential separation between the ADD and the affine ADD. Okay? Not only in the representation, but also in the operations. If I add two functions like this, it takes me linear time to produce the result, even though the result as an ADD is exponential. If I multiply two functions like this, I can compute the result in linear time. Okay? Whereas, again, it's exponential for the ADD. Now, the operations are quite painful to implement in practice. And so if you want to use affine ADDs, I just suggest using my code for doing it. But the key is that you have to do some pre-normalization before you do an apply operation, because you want to identify all possible reuses of previous computations. I'm going to refer you to the paper or email me for the details. Not something I want to cover in this tutorial. Okay, so here's an additive function. As we pointed out previously, so this doesn't have the exponentially increasing coefficients. It's just additive. So I only have values from 0 to the number of variables. If I have 5 variables, I have values from 0 to 5, just counting the number of x1s, of xi's that are true. So if all are true, I get count 5. If all are false, I get count 0. And anywhere in between, I get some other value. So this function is a quadratically sized ADD. And again, it's a linearly sized affine ADD. Okay. This function is sum over I to the ixi. This is the worst case, has an exponential number of leaves. And again, linearly sized affine ADD. Okay. Now, this is just one quick example for those who do constraint programming. So I guess I didn't mention, but constraint programming would be another place where you might be able to represent decision diagram representations of functions. So here's a factor graph. And imagine I have constraints between variables x1 and x2, constraint between x2 and x4, constraint between x4 and x3, and between x1 and x3. So I sort of have constraints in some cycle of variables. So imagine the constraints were actually values. I get a value for different configurations. And I just want to sum over the values of all constraints. So kind of like soft constraints, perhaps. It's rather cool that if you look at the ADD, you don't really see any structure. But if I sum these pairwise functions, right? So for every orangish block here, I get a pairwise function. If I sum these pairwise functions, you get this very clean-looking affine ADD. Okay. And one question is x1 to the top and x4. This is for some from x1 to x7 of pairwise functions. One question is, why does it branch in the beginning and then only reconverge the branch at the end? So basically, this structure here is encoding the pairwise interaction between x2 and x3, x3 and x4, x4 and x5. So you would expect this sort of locally linear structure to encode interactions between. But why did why did I branch initially into these two branches and only reconverge at the very end? So I'll tell you, if I didn't have a cycle here, if I broke the cycle, you wouldn't have this, these two separate branches. But it's because if I go x1, x2, x3, x4 in a cycle, by the time I get back to the last variable, the last constraint, I had to record which value of x1 I had. Right? Was it true when I look at x7, or was it false when I look at x7? And that's why I get these two branches. So it's rather cool that when you use affine ADDs and you have these very structured functions, the structure comes out immediately in the affine ADD, whereas in the ADD you didn't have any structure. So I haven't yet used these for constraint sort of problems, but I would like to because I've seen a lot of structure here. So very cool functions, theorems that they're canonical, they're minimal, and that they can yield an exponential time space improvement over the ADD. However, there's one major caveat. The ADD had a polynomial bound on the apply operation complexity. However, the affine ADD doesn't have that polynomial bound. Things can go up exponentially. And the quick reason is because the affine ADD can have this reconvergent branch to the same subdiagram. And in some worst cases, you can see an exponential blow up. But it's always upper bounded by the ADD. The affine ADD provably will never do worse than the ADD, because there's always a trivial setting of the affine transforms that gives you back the ADD, and we always know we're smaller and more efficient than that. So basically, the key thing in practice is that you will never lose in theory by using the ADD versus the affine ADD. Always more compact, always more efficient for the operations. However, I wouldn't say that affine ADDs are a universal replacement for ADDs for the reason that you're doing tons of multiplies and divides. And in practice, I've run into lots of problems with numerical precision. So if I get an affine ADD over 30 variables typically, and you've got 30 divides from the leaf up to the root, you can get enough numerical error in those 30 divides that can actually throw off the structure quite a bit. And if anyone has expertise in numerical error, please talk to me, because for ever since 2005, this problem's vexed me. And it's ruined a year of some PhD students' lives without a solution. So it's useful as long as you have local structure. If you need a function over 30 variables directly, it's not always the best thing. OK, so I've got about 5 minutes, maybe a little bit more. So I'm going to wrap up with some other decision diagrams. I said earlier that everything I talked about in this tutorial also applied to non-Boolean domains. Okay? Because if I have this robot example from the very beginning, where the robot could be in room 1 through room 6, I just need 6 branches, right, for every possible value of r. Right? And it's quite trivial to extend all the algorithms I talked about previously just to branch k times rather than 2 times. Right? So that's rather easy. This is called the multi-value decision diagram, but I mean it's just equivalent roughly to the ADD. Okay. There was the multi-terminal BDD. This is mainly used in the verification literature where you have like multipliers and adders and you have bit vectors. And they basically just said, rather than having bit 1, bit 2, bit 3 as different functions, you can just sort of concatenate these on one bit string at the leaves. But really, the ADD just gives you any node here, be it real or integer or Boolean. So the ADD sort of already subsumes this. Now you have things called the factor edge value BDD. So it turns out when we did the affine ADDs, people had done some work previously for stuff like this with integer functions. However, it's different. It's quite different from the affine transform that I showed you previously. When you have integer functions, the way you define canonicity is with prime factorizations. So you subtract off a constant, but then to do the canonical edge transform, you use a factorization. So it's quite different in nature than the affine ADD. But again, it's trying to exploit additivity and multiplicativity in integer value diagrams, if you happen to have that subset. Okay, and recently, my recent work since 2011 has been working with continuous extension of decision diagrams. I've previously worked on some lifted and some relational extensions. I'm not going to talk about those, but I will talk about some continuous extensions, just briefly in 2 slides. So basically, if you have functions which have which have continuous variables in them. Now your decisions can be inequalities, not just linear inequalities, but they could be nonlinear if you wanted, right? And the inequalities can be true or false. Okay? And the leaves can now be expressions, not just constant values, but expressions of your variables. So this function here is a decision diagram over continuous variables x1, k, and x2. Okay? But it's pretty obvious that if I have values for x1, k, and x2, I can evaluate a path from root to leaf, and then evaluate the expression at the leaf. Right? So this comes up a lot in continuous planning, where you get functions like this. So if I just want to show you what happens when you have an XADD like this. How would I do a max operation on these two functions? Okay. So again, you have to have an ordering over decisions. Decisions are now these complex inequalities. However, if they're linear inequalities, you can always identify unique decisions, right? If I give you a linear inequality, I can tell you whether it's equivalent to another linear inequality or not. So you can identify you can assign a ID to every test, every inequality, and then you can order them. So let's assume that y greater than 0 occurs earlier in the order than x greater than 0. Right, so I need to recurse on y greater than 0 first. Okay, if that's true, I get the max of x, which is a free variable. It's a continuous variable x. Get the max of x and this function. Okay, I don't know the answer, so I'm going to recurse on this decision. Right, so now I have the max of x, and if x greater than 0 is true, of y, max of x and y. Unfortunately, I still don't know what the max of x and y is. Right? I mean, I can't just what I don't want to do, if I only want to allow arithmetic expressions at the leaves, I don't want to put max of x comma y at the leaf, right? So am I stuck? Turns out in practice, no, right? Because you can do this. If x is greater than y, then you know x is maximal. And if x is less than y, then you know y is maximal. So you can extend all of the previous discrete decision diagram operations to continuous operations as long as, in the special case of max and min, when you hit the leaves, you introduce new inequalities. Okay? But I will say the one complexity that you end up with when you go to continuous decision diagrams, well, you get many complexities. But one is that you're always introducing new decision tests. Right? So your functions can become very, very deep in terms of the number of decisions. There's no sort of bound other than the number of operations you've done on how many decisions you can have from root to leaf. So that's one problem that you have to control in practice. The other is now the decisions are no longer necessarily independent. Right? So you actually have to do some constraint pruning along the paths. And so that's one other source of inefficiency. But in practice, you can do this. And in continuous cases, you can solve a lot of interesting problems with it. Okay. So talk to me if this interests you. It's more recent work. I do have code online for both Affine ADDs and XADDs if you actually want to play with this in practice. OK, I'm going to give you one approximation idea, and then I'm going to wrap up. So often in practice, your decision diagrams do grow large, right? You just can't control that. But you can approximate within some epsilon error bound pretty easily, especially if it's an ADD. So imagine that I have this function, sum of I equals 1 to 3 of 2 to the I xi. And I add in this additional variable, which is some epsilon noise, some very small value, 0.001 times x4. Well, unfortunately, for every path from root to leaf, I'm going to get a different value, like 3.03, 3.07, right? Different values that they have to be different leaves. If I want to compress this with an epsilon error, say, of 0.1, is there some really obvious way to do that?
Compress the two adjacent leaves.
Yep. Exactly. Yep. So just do a search over all your leaves, try to find when they can be merged within some epsilon error. That's pretty easy. It's quite like time in the worst case, but there's some greedy algorithms that are a bit more efficient. So you can merge all these nodes, right? And then once you've merged them, you just call the reduce algorithm to create the canonical result. Okay? And you get this result, which is within whatever your merge error was here, right? The result is within epsilon of that merge error. So this is called the apricot trick. It's from this paper in NIPS 2000, and it's quite effective in practice for taking large diagrams and compressing them very efficiently. with bounded error, which is great. So you always know the error that you've induced. Okay, there are extensions of that for Affine ADDs. I'm not going to cover that. It's in the slides if you want to look at it. And in practice, I mean, you know, I'll just show you one slide on results. Just some different operations. I'm showing you the running time on the top graphs and the amount of space, number of nodes on the bottom graphs. On the x-axis, I'm scaling the number of variables in these functions that I'm either adding or multiplying. And at the top, I have the table. And then the next line down is the ADD, and the next line down is the Affine ADD. Now, I did choose functions here that were the optimal exponential reduction for Affine ADDs. So this is to show off the performance of Affine ADDs. But basically, you see that you're never losing by using the ADD. And the Affine ADD is always even better.
So I just want to confirm with that. So what you said and what the diagram showed seems to be different. So you were saying that the top curve is the table.
I did lie, yeah, in some cases, sorry. Yes, OK. Sorry. Sorry, trust the diagram.
Okay.
Sorry, right. So actually, so sorry. Yeah, thanks for pointing that out. In any other random function, what I said would be true. The ADD would be more compact than the table, more or less, and the Affine ADD would be more compact. These functions here are the worst case for ADDs. They're always exponentially sized, right? Every leaf value is different. So certainly, you're going to pay an overhead for having the ADD. The table is more efficient in that case. Now, why is the space larger? It's because the table only had to represent the leaf values, whereas the ADD had all the internal nodes to get to the leaf values. So actually, yeah, this was the worst case for the ADD. But in practice, I would say you don't see this. But it was the best case for the Affine ADD. This is not.
Can the AADD ever be worse than the table?
No. So in terms of space, the Affine ADD is upper bounded by the ADD. Given that there is this 2 times, the ADD can be twice as large as the table if it was exponentially sized. So I guess in the worst case, the Affine ADD would be within worst case 2 times the size of the table. But again, I haven't really seen cases where that occurs. You have to construct them. OK. I mentioned that I would talk about compilations, and so I'll mention that as briefly as I can. There are these ways to construct. OK, the thing with decision diagrams is they're meant for efficient operations. Conjunction, disjunction, if it's stats, intersection, union, if it's ADDs, addition, subtraction, multiplication. And when you're doing progression, regression, in planning problems, you often need to do these operations on functions. However, if you were just doing satisfiability, right, or constraint solving, you might not actually need to do these operations in practice, right? You don't have some horizon that's indefinite that you're planning for. So if you can just do all of your operations, all your sums, all of your conjunctions up front, right, then you can do what's called compilation. And that's where things like the knowledge compilations of Darwich come from. And there is this very beautiful paper by Darwich that shows this hierarchy of compilations, from negation normal form down to some restrictions of ordered binary decision diagrams. So what Darwich calls the OBDD, the order BDD, I just call it BDD. Most people do in practice. And basically, what he proves is that the size of compilation, this D, and an F, is strictly less than or equal to the size of the BDD. Okay? So it means if you can do all of your operations up front, your conjunctions, your disjunctions up front, then you will get a smaller result than if you had done all the operations up front with the BDD. If you're doing things like satisfiability, you can do all your conjunctions and disjunctions up front. Right? Then you just have to search for the satisfying solution once you've done the compilation. So if you know in advance all operations that you have to do, then you should consider a compilation. However, if you're a planner and you have an indefinite horizon and you don't know how many operations you have to do to get to a solution, to get to your goal, then you do need to do more operations as you go on. And the thing with the things like D, and an F is that you can't do plus and times efficiently on them. you can compile functions into these forms that use plus and times, but you can't take two DNF functions and multiply or add them together efficiently. I think you can do addition efficiently, but you can't do multiplication. So there's some operations you can do. And so it depends on your use case. But again, if you know in advance all operations you have to do, then you should definitely take a look at this paper and the compilations and some really amazing software that Darwich has put out from his group at UCLA. OK. And everything's all in the slides if you want to look at this later. OK. So that's a crash course in decision diagrams. Hopefully you guys learned a bit today. So I mean, the main point I want to say is if your problem is factored and you're currently using tabular representation or enumerating, right, all possibilities, but you need binary operations on these factors, then consider using a decision diagram instead. I'm going to claim in practice you're not going to use anything, you're not going to lose anything by using a decision diagram. And somewhere here I had software, darn it. There is some amazing software. If you need ADDs, sorry, one sec. Let's see if I can just find the slide real quickly. Well, sorry guys, it's in the slide somewhere. I can't find it on. There is great software if you're just using ADDs or BDDs. There's software called CUD, the Colorado University Decision Diagram Package, written in C. It is bit hacked. You don't want to read the code, but it is obscenely efficient. The most efficient implementation I have has only come within 10 times the speed of CUD. So there are amazing packages. It'll be in the slides if I can find what's. It'll be somewhere in the slides when I post these online. But there are amazing packages online for BDDs and ADDs. If you want to use some of the extensions, like the continuous extension or the Affine extension, then I've got software on my webpage for working with those extensions. If you have any problems using that, just send me an email. But you know, if you're using tables or you're enumerating, and there's more structure to exploit, definitely consider using decision diagrams. And there's amazing software online that's obscenely fast that you can use without having to code it yourself. Okay, and with that, thank you guys. Any questions? We're just at the time limit, but I'll take a question or two. Pedro? Take the mic first.
So for example, if you're trying to compute like policies for, so I think you told me that, but I just want to confirm. So this could be naturally used for like compiling policies for like MDPs and POMDPs in like a compact form? Yeah, because if your leaves are the, you know, if you assign an ID to every action, right, then your leaves are like integers. So you just use the ADD for that. Okay. And then if multiple paths converge to the same action, right, then you get the compactness. Okay. Okay, everyone else? Wait, one more question.
Is it possible to perform substitution of the BDDs, one BDD into another efficiently?
That's a good question. So can you substitute in for say one variable in a BDD? Yeah. If you define the variable equivalent to an entire other BDD, could you substitute that in? Yes, although you won't find it in the literature. But I can tell you how to efficiently do that with the apply operation. But talk to me offline. Yeah. Okay. Good. Yep.
So imagine that you weren't using grounded representations of the operators in plan.
Oh, yes. Great question.
You're using lifted representations of the operators. Is there some way?
Yes. Okay. So the question was, if you had if you didn't want to ground out the variables, say in a riddle or PDDL representation, how would you exploit the structure in a decision diagram without grounding? And let me find quickly the slide where I talk about XADDs. Sorry, here we go. Sorry. So there's these things called first-order decision diagrams, and in my thesis, first-order algebraic decision diagrams. And the idea basically is replace these inequalities with a logical formula. They could have free variables. They might not have, might not have free variables. If you do this, then you get these first-order diagrams, and you can do now. So Ronnie Cardon and his students have done one variant, which is very cool, and can be much more compact than first-order ADDs. I'm doing a different variant with the first-order ADDs that isn't always provably as compact, but has a canonical form, whereas Ronnie's FODs don't typically have a canonical form. So we have two competing variations in the literature that you can look at. But yes, it's just this idea, but except the tests are now logical expressions with or without free variables.
So like what they did in production systems, decades ago, was use reading nets.
Yep.
And they used tokens to gather up instantiation of the variables.
Yep.
Do you have to do something like that here in order to construct what the instantiation would be that satisfies those tests?
Well, I've got, the answer is quite long. We'll take this offline. I actually have to do theorem proving in practice. So I have to do theorem proving, and Ronnie doesn't, so that's a difference. But if you've ever worked in theorem proving, there's a theorem proving called Vampire, which is aptly named. So it is actually, theorem proving scares most people, but actually it shouldn't scare you as much as this sounds. OK, I hear lots of zippers. I think it's past time, so I'm going to let everyone go. But again, thank you for coming to the tutorial.